In exercise 6.4, we had a chance to talk about the fact that stuff spreads out. If you assume that everything happens by pure chance, only one thing ever happens. Stuff spreads out. If you had 4 molecules on one side of a container, there's only one way that those 4 molecules can all exist on one side of the container. But there are 4 ways that you could have one molecule on the other side. Either one of the purple molecule, or the yellow molecule, or the orange molecule, or the green molecule. So there's only one way that they can all be on one side. There are 4 ways that one of them can be on the other side, and so it's more likely that one of them is going to be on the other side rather than them all staying in one place. Now that's if you had 4 molecules, but think of the galactic scale that we exist on. Every time you exhale, you breathe out more atoms than there are stars in our galaxy. If you were to go to the beach and go to the ocean, instead of seeing water, you saw blueberries. All the space that the ocean is taking up, not only the Atlantic Ocean, but the ocean all over the world. Imagine that's entirely filled up by blueberries. From the very depths of the ocean to the very top surface of the water, all blueberries. That number of blueberries is smaller than the number of water molecules in one drop of water. You can hold a mole of carbon atoms in the palm of your hand, and yet a mole of peas, like you eat for dinner, a mole of peas would cover the entire surface of the Earth 900 feet deep. So we, at our galactic scale, what if you had a mole of gas molecules? 6.022 times 10 to the 23rd gas molecules on the left there. Well, there's only one way they can all exist on the left, but there are 6.022 times 10 to the 23rd ways that you could have one of them go to the right. And so one always goes to the right. There are even more ways you could have 2 go to the right. And so what ends up happening is that the numbers of atoms become so large that a thing that just looked probable when you only had 4 molecules becomes deterministic when you have so many. You have so many molecules, there are so many ways they can spread out, and there's only one way that they would all stay together, that they always spread out. There's not enough time in the history of the universe for the chance of them all staying together to ever be realized, because there are so many ways that they can spread out. So stuff spreads out, and that by itself doesn't sound like the most profound like one of the most profound ideas in science, but it explains a lot. It explains, for example, why the universe is expanding. All of the stuff in the universe, every day the universe is bigger than it was the day before. Not only that, but every day the universe is expanding faster than it was expanding the day before. Stuff is spreading out as a whole in our universe. That also, the fact that stuff spreads out also gives a direction to time. There are some things that you can do, some things that existed a certain way in the past, you can change them, and you can move them exactly the way they were in the past. For example, if you have a cup on a table, move it over, and then you can move it exactly to how it was in the past. You can move it back. Because nothing's spread out in that process. But some things you can't make like they were in the past. If you put creamer in your coffee, after it spreads out, there's no way to get the creamer all back together again, spontaneously. It will never happen. Things like, any time that anything spreads out, that process can't be undone. So if I were to show you a video of the Earth rotating around the sun, it would be hard for you to know exactly whether I was playing it forwards or backwards, because something going in a circle, nothing is spreading out, there's no direction to the time there. And anything that's happening can unhappen in that change. But if something spreads out, if I show a video of you putting a drop of dye in water, you know immediately whether it's playing forwards or backwards. If the dye spreads out, you know it's playing forwards, and if all the dye comes back into one drop, you know it's playing backwards. The fact that once stuff is spread out as a whole, it cannot come back together again, that gives a direction to time, that gives a meaning to the words past and future. So this principle of stuff spreading out doesn't only explain how our universe as a whole is behaving, it also gives a direction to time and makes the some things that exist in the past unable to ever be reproduced again. It's also the motor behind all life. When you take a biology class and they talk about things moving inside of a cell, they say, oh, this hormone enters the cell and then moves into the nucleus to affect your genes, or the mRNA inside of your nucleus moves outside of the cell and goes to a ribosome so that you can make proteins. All of that movement inside of a cell is happening because every type of molecule in the cell is constantly spreading out until it's homogeneous. And so anything that is made on one side of the cell spreads out until it's everywhere in the cell. If something is made like mRNA in the nucleus, it spreads out until it's everywhere in the cell, including on the outside where the ribosomes are. All of the movement inside of cells, the motor behind all of that movement that is the basis of life, is just the fact that stuff tends to spread out. So those are big things, and that's the reason why cells are the size they are. You never see gigantic cells the size of a baseball or a basketball or the size of a car. Cells are all microscopic, and to make bigger creatures, they have to come together to form tissues because all of the movement inside of them is based on diffusion, is based on stuff spreading out, but that takes time. If you can put a drop of dye in a cup of water and you can see it takes minutes for it to spread out. Well, cells don't have that time. They can't wait for the mRNA inside of the nucleus. They can't wait minutes for that to get to a ribosome. So the size of a cell is limited by the fact that stuff spreads out, and the fact that you have tissues and organs and your cells are so small that you can't see them with your eye, that again is because stuff spreads out. Plants take up water. You have a 300-foot sequoia tree. It has to take water up to its leaves 300 feet in the air against gravity. How does that happen? Well, you have all the sugar being made in the leaves. You have all of the water in the ground. Right now, all of the sugar is in one place, all the water's in one place. What happens? They start spreading out. They spread out until they mix completely. And so the leaves fill with water, and you can see the leaves getting larger in spring because the water is entering the leaves and filling them up and making them firmer because of stuff spreading out. And the sugar goes down into the roots, and so you get these roots with a whole bunch of sugar in them. Root vegetables, think of like carrots or potatoes. How did all that sugar get into the roots? It was made in the leaves, and it's spread out. Oxygen gets into our bloods. When you breathe in, it just brings the oxygen it brings the air into little sacs inside of your lungs. How does it get into your blood? Once it's there, it spreads out into your blood. And the waste product that you make when you break stuff down, that waste product gets into your urine and your kidneys because it spreads out into water that is less concentrated which ends up being your urine. So a whole bunch of things are explained by this principle that stuff spreads out. And we talked about some fundamental things, but in the context of chemistry, the fact that any reaction ever happens at all is also caused by stuff spreading out. And that's what they're trying to get at in exercise 6.5. They say at room temperature, molecules spend most of their time in lower energy conformations. In fact, there's a general tendency for any system to move toward lower energy. As another example, electrons form bonds because they supposedly prefer, but of course they don't have feelings, they don't prefer, they just achieve a lower energy state. And now we can appreciate the reason. It's based on entropy. When a molecule assumes a lower energy conformation or when electrons assume a lower energy state, the entropy of the total system, that's what that TOT is standing for, increases. And they want you to explain. Well, the stuff that spreads out is not just atoms and molecules, it's energy too. And we saw that in the previous exercise. When energy spreads out as heat, that makes a reaction more likely. Well, imagine the energy spreading out in a molecule. So, for example, with resonance, if you have a positive charge on an alkane versus a positive charge that's allylic, this is more stable. Why? Well, it's a resonance form, so this can go there, and the positive charge ends up spreading out. The true molecule ends up looking something like this, with the positive charge spread out. And when the positive charge is spread out, that's a more likely way for that charge to exist than all forced in one place. When energy is forced in a small space, it becomes reactive. Why? Because there are fewer ways it can exist in a small space, and so it's less likely to happen. When it reacts, the charge gets spread out. If it forms a new bond, that charge is now spread in between that atom that it's on right now and the new atom that's there. And so the charge gets spread out when you form new bonds, when you form reactions. High energy molecules don't have any mysterious power to them. They're just arrangements of stuff that can only be arranged in a few ways. A high energy arrangement is an arrangement that can only happen in a small number of ways. And so as chance takes its toll, those things that only happen in a small number of ways happen less and less often. And that's why high energy molecules change into lower energy molecules, molecules that have their energy more spread out, molecules that can exist in more ways, and so that are more likely to exist. So this principle of stuff spreading out doesn't just explain a lot of stuff in the universe, it explains why any reaction happens ever in all of chemistry. Because the energy in the molecule spreads out by the reaction happening. And so this exercise 6.5 is really just talking about the significance of this funny principle, based on pure probability, pure chance. But in chemistry, you have such enormous sample sizes that what was just chance becomes determinism. Stuff always spreads out, and it explains almost everything that happens in our universe.